Hey there folks, welcome back to my channel. Today we're talking about Norton equivalent circuit. Now a quick question for everyone. How many of you have heard about Norton equivalent circuits before? And do you know how to calculate it? Well, in this video and for exercise 1.37 from the Art of Electronics 3rd edition, we are going through the calculation of a simple potential divider and representing it with the Norton equivalent circuit. So what exactly is the Norton equivalent circuit? Well, imagine you have a complex network of resistors, capacitors, and other components. When analyzing these components, it can be quite difficult to analyze a complex circuit with multiple resistors or capacitors, especially if you're trying to simplify the circuit. So that's where the Norton equivalent circuit would come in. It's a way of simplifying a complex circuit into a much simpler form with just a current source and a resistor. What you are doing is representing the complex circuit with two components, a current source and a resistor. So that's what we'll be doing in this question. First of all, let's talk about the question itself. So in the book, it says find the Norton equivalent circuit, and in brackets you've got a current source in parallel with the resistor for the voltage divider in figure 1.134. Show that the Norton equivalent circuit gives the same output voltage as the actual circuit when loaded by a 5K resistor. So the circuit that the question is talking about is the one on the screen now. So you've got a 10 volt power supply, a 10K resistor, and a 10K resistor in series. The load is in parallel with R2. So let's first of all find the Norton current. In order to do this, you need to short out the load. So what you're doing is changing the load resistor to 0 ohms, essentially removing this from the equation as the parallel combination of the two resistors is equal to 0. And then you can calculate the current through this circuit. So obviously you got 0 ohms there, so all the voltage drop will be against this 10K resistor over here. So you got 10 volts divided by R1, which is 10,000. So 10 divided by 10,000 is 1 milliamp. After calculating the Norton current, we can find the Norton resistance. And in order to do this, we need to short out the power supply, and then we calculate the resistance looking into the load nodes. So that would be from here to here. So imagine this power supply is shorted out. So we have a straight wire to ground and we're looking into this node. So we see this R2 is connected to ground here and this R1 is connected to ground here. So we have two 10K resistors in parallel for which the combined resistance is 5 kilo ohms, using the 1 over RT equals 1 over R1 plus 1 over R2 equation. So now we can represent that circuit using the circuit on the screen now. So we have a current source. The current source is going to be pushing out 1 milliamp of current, and we have a parallel resistor equal to 5 kilo ohms. R5 is representing some load. Just showing the two circuits side by side again, we have the original circuit that was given to us by the question, a potential divider with R1 and R2 with a 10 volt supply, and the Norton equivalent circuit is a 1 milliamp current with a 5 kilo ohm parallel resistor. For the second part of the question, we need to check the output of this circuit with a 5 kilo ohm resistor load. So basically we're changing this load resistor to 5 kilo ohms in both cases, and we need to check the voltage on this node over here, which is the output node. And if our calculations were correct, we should get the same output voltage on both of those nodes. So let's check that on the simulation software now. So I've drawn the circuit from the question over here on the left hand side and the Norton equivalent circuit on the right hand side. In order to make a current source work on LT Spice, which is the simulation software I'm using over here, we need to have a second voltage source. I've set the value of that voltage source to 0, but then the current source is basically a function of this voltage source. So what I've done is basically this node over here is V in brackets in, and I've added 1 milliamp to it. So this should be pushing out a constant current of 1 milliamp. We have two 5K resistor loads, so that's R3 and R5 in both circuits, and I'm doing the circuit simulation over 1 second. Now first of all, let's check that the current source is actually producing 1 milliamp of current. So to check the current, I'm just clicking on this node here. You can see you've got a current loop, which you normally use to check current, and a arrow going through it. So you've got 1 milliamp of current going through there. And obviously that's going in this direction and will split between the two resistors. Then by clicking this node here, we can check the output voltage, which is equal to 2.5 volts. In this circuit, obviously we have 10 volt input, which is from the question itself. And we have the two 10k resistors and our 5k load. If the equivalent circuit is accurate, we should also have 2.5 volts here. So you can see that is equal to 2.5 volts as well. So both of these are identical in the output voltage they produce. So you can see the advantage of doing this is basically simplifying a complex circuit into a simpler version of itself for analysis. So doing this calculation obviously is a lot easier than doing the calculation across this. Now, if you imagine this on a resistor network that's significantly larger, and then turning that into something like this would make your life a lot easier when you're trying to calculate outputs or trying to analyze the circuit. So thank you for watching my video today. If you have any comments or questions, please leave them in the description below, and don't forget to like or share this video. Thank you.